Hello everyone, welcome to my marine seismic data processing course. In this presentation, I'm going to talk about the concept of convolution in terms of seismic data processing. So in this presentation, the content of this presentation is I will start with a brief introduction about convolution, the mathematical implementation, the mechanics of the convolution process with some examples, the properties of convolution, the applications of convolution, and the summary. Okay, so basically convolution is defined as a filtering operation of one waveform or the filter over the other. So, and the resultant will be a change of shape of a waveform. So as you can see on the right, a source wavelet is convolved with a reflectivity series with two spikes. So the resultant will look like that. So this is a convolution process, and if these two spikes are very close to each other, the resultant will be the summation of the two waveforms in the overlap area. So the waveform will look a bit different this time. So if you have quite a lot of spikes in your reflectivity series, your resultant will be the summation of the resultant of the waveforms after passing through these spikes. So in terms of mathematics, it's written as g of t star f of t. This asterisk sign denotes the convolution operation, and the g of t and f of t are two functions, and their convolution in time will be written as y of t. Okay, so in terms of mathematical implementation, so basically when we convolve two functions, we time invert one of the function and progressively slide past over the other function, and while sliding past the other function, each time we cross multiply the terms over the overlapping parts of the two functions. For example, if you have a function g of I with the elements from 1 to m, and another function f of j with elements 1 to n, and when you convolve, your final output will be written like that. I will explain that with an example, it will be more clear. So another thing is that if you have g of I with length m with m terms and f of j with n terms, your final convolved product will have the length m plus n minus 1. Okay, so what it means, let's go through an example. Yeah, I will go to that example before, but let's discuss the mechanics of the convolution process. So let's say that you have a function a with the elements a0, a1, a2, a3 up to a7, and another function b with elements b0, v1, b2. So we first fixed one of the array. So let's say we fixed the array a with elements a0 to a7, like written like that here, and then then assume that the moving array is b0, b1, b2. So like I said, we first time invert the function. So instead of b0, b1, b2, we write it as b2, b1, b0 with b0 at the front, and then we start sliding over the other function, the fixed array, and every time we have to do the cross multiplication of the terms in vertical direction. So for example, for this one, you have c0 will be equal to b0 times a0, and then c1 will be equal to b1 times a0 plus b0 times a1. Like that you will do all the terms. So that formula we have seen in the previous slide will be written like that. So if in terms of real example, so let's say we have a signal with the length 4 with the 4 elements -1, 3, -2, -1, and is convolved with the filter operator 2, 3, 1. What is the convolved output? So first thing is you have 4 terms here and 3 terms here, so your output will be 4 plus 3 7 minus 1 6. So your output length will be 6 elements in your output. So first thing is you have to reverse the order of your terms in your filter operator. So instead of writing 2 3 1, we write 1 3 2, and then we start sliding past the other function, which is the fixed array or fixed function. So the first term will be 2 times -1, gives you -2. The second time you slide past is 3 times -1, and then 2 times 3, so it will give you -3 plus 6 equals +3. And similarly, slide the third time, you will get 1 times -1, 3 times 3, and 2 times -2, and then you add them together, you will get 4. For the next time you do the same, so your final convolved output will be -2, 3, 4, -5, -5, -1. So this is how convolution process works. This is another similar example. So again, you have four terms in your signal, so 4, 3, 2, 1, and then 2, 0, 1. So your final convolved output will be 4 plus 3 7 minus 1 equals 6. So you will have 6 elements here, and instead of writing 2 0 1, you write it as 1 0 2, and then you start sliding past the other fixed function, and then you do the cross multiplication in vertical direction, and then you do the summation. So that will be your final output. Okay, so in terms of the properties, there are two main properties of convolution. First property is commutative. So convolution is commutative. What it means is if you convolve A convolve B or B convolve A, it will be the same output. So here in this example, if you convolve 1, -1 over 2 with 1, 0, 1 by 2, your convolved output is this. And if you convolve 1, 0, 1 by 2 with the source wavelet 1, -1 by 2, your convolved output is this. So basically they are both the same. So it doesn't matter if you convolve trace A with trace B or trace B with trace A, you will get the same output. Second property, this has been already discussed in the 1D Fourier transform lecture, but I will explain to you again. So basically convolution of two functions in time domain becomes laborious as you increase the length of the function. So in order to avoid increasingly laborious convolution process, we do the convolution in time, but we do transform the functions in frequency domain and then perform the convolution process there. So basically convolution in time is equivalent to multiplication of amplitudes in frequency domain and the summation of the phase spectra. And then once we do this in frequency domain, we transform back in time domain, and we will get the same output as you will be doing in time. What it means is if, for example, if you convolve h of t with g of t, the functions in frequency domain are written as like that, and then once you simplify, you will get a1 multiplied with a2, and you are adding the phases phi1 plus phi2. So this is another important property. So instead of doing things in time, we normally do in frequency domain and then transform back in time domain. Okay, so in terms of the application, so one most important application is filtering. So basically every filtering process involves convolution. So any two traces convolved with each other or a filter convolved with another trace is basically convolution process. So every filtering operation is a convolution. Another important application is in surface related multiple elimination process. It's called SRME. So basically before going in detail, I would like to explain this this diagram here. So you have the source, the receiver, this is the sea surface, and this is the seabed. So the green arrows represents the primary signal from the source reflection from the seabed and then received at the receiver. And then you have another event, so your primary is, this is known as the primary, the green signal, so primary is represented here. And then you have another event, it goes like that and then get reflected from the seabed, and then it's get reflected back from the sea surface, and it changes its polarity, so it's recorded here. So the multiple is recorded with a negative polarity because you have a contrast of impedance at the sea surface. So the distance between the source and the receiver is called as offset. So this the time of the primary and the time of the multiple, it will be twice if we assume it's zero offset. If we assume that the source and the receiver are at the same location, so it will be just vertical. So if it's zero offset time, it will be exact double of the primary event. Okay, so in SRME is basically involves convolution of data with itself. So for example, if you have a trace like that, so you have primary first event P1 and the multiple. Just for simplicity, I have assumed that it has the same polarity and the amplitude is represented by 1, so M1, and then P2 is another primary event. So if you convolve this with itself, so data convolve with itself gives you the multiple model. This is the basic principle of SRME. I don't want to go in much detail of the SRME process here because it will be covered in full details in the SRME presentation. So let's just start the convolution process, what we have seen before. So we first flip this function here, so we flip like that and then we start sliding past. So at time t0, so you have 0 amplitude, 0, so when you convolve 0 with 0 you will get a 0 here, right? Then you slide past one t1 time, so now you have 1 multiplied with 0, you do the cross multiplication in the summation, 1 multiplied with 0 plus 0 multiplied with 1, again it will give you 0. So at t1 time still you have 0 amplitude. Now again you slide past. So now you have at t2 time 1 times 0 plus 1 times 1 plus 0 times 1, so it will be just 1 times 1, so you will get output as 1. You slide past again one step further, so now you have 0 times 1 plus 1 times 1 plus 1 times 1, and the others 0 times 0, so you will get 1 times 1 plus 1 times 1 equals 2. Now further you will get, again you do the cross multiply, now they are 1 times 1 plus 1 times 1 plus 1 times 1, so you will get the resultant 3. So basically this this event in your convolved output is basically the multiple timing of the multiple. Of course the amplitudes will not be the same as the multiple recorded in your data, but we do some once you have the multiple model, we do adaptive subtraction in your processing sequence to adapt the multiple amplitude as recorded in your data. So basically when you convolve this data with itself, you will get the multiple M1, and then of course you will get the higher order multiples further down in your trace. So this is one of the very important application of convolution. Okay, so in terms of the summary, convolution is basically a filtering operation of one function over the other. So every filtering operation is convolution. The second point is the recorded seismic trace is basically a convolution. So basically you generate a signature, a source signature. For example, in marine case you use the air gun signature and you convolve with the Earth's reflectivity series, and what you record as a seismic trace is basically the convolution of the source wavelet with the Earth's reflectivity series plus some noise. So that's what you record in your seismic trace. The third point is convolution is commutative. It doesn't matter if you convolve FT with GT or GT with FT, you will get the same output, and the length will be the same. The length of your output will be the same. The third point is convolution in time domain is basically multiplication in frequency domain, and in frequency domain you basically multiply the amplitudes and add the phase for each of the frequencies. The last point is the application of convolution in SRME is very useful to drive the multiple model. Okay, I hope you enjoyed learning this important concept of convolution. So these are the two books I have used in my presentation as a reference. So if you would like to visit any of the topic in detail, you can refer to these books. Thank you very much. Take care. Bye-bye.